this info day is related to the universal challenges 1 and challenge 2, and of course to the case study 2, which is related to forestry. We'll have the presenters today, Stefan, Emand, and Thor. So I will give the floor to Stefan to have the first presentation. Please, Stefan, feel free.
Hello. Hey, just let me share my screen here 1 second. Right, can everyone see my screen?
Yes.
And now can you see it in presenter?
Yes.
Yes, okay, great. All right, so I'll be presenting on behalf of SPADE for the forestry case study. The first challenge I'm going to go over is the swarm communication and navigation challenge. My name's Stefan Lloyd. I'm with Norwegian Institute of Bioeconomy Research, NIBIO, and we do forestry research in Norway. So the forestry case study in SPADE looks to test the use of drones for forestry management. And forestry operations rely on continuous detailed inventory and monitoring of forests. So for the swarm communication and navigation challenge, we are looking at using drones to map and measure forests below the canopy. Right now, it's quite easy to use drones to scan forests above the canopy, but with that kind of approach, you miss a lot of the lower portions of the forest. So we want to get in below the canopy and do measuring that way. So in a previous open call challenge that is just wrapping up now from last year, we have already developed software and technology to basically use a drone to map and navigate below canopy with a single drone. And that solution uses a graph slam approach with LiDAR inertial odometry, GNSS loop closures. It uses an occupancy grid approach to do collision avoidance with the trees, and it's able to just basically follow waypoints over a ROS interface as best it can. So if you give it a waypoint, it will try to get to a waypoint while still avoiding collisions with the trees and mapping of the environment. So for this open call specifically, what we're looking at doing is expanding the work from this open call to a drone swarm as opposed to just an individual drone. So the objectives are to enable swarm exploration and mapping of below canopy forest environment. So this will involve developing robust inter-drone communications, assembling a global LiDAR map from multiple drone swarms, from all the different drone swarm participants, and then also coordinating the drones, at least the navigational commands to each of the drones, to get them to collect sensor data from all the different areas of the map that need to be mapped. And then as the output to this algorithm, basically what we need is a point cloud that is stitched together from all different point cloud, from all the different swarm participants as a single LAS file in global coordinates. And the point cloud should be stitched together from all the different disparate swarm participants in a smooth manner. So there can't be like a seam at the intersection of the different point clouds where they don't match up perfectly, and you get maybe one tree represented as two trees in the point cloud. It needs to be done in a very smooth manner, so you get one single cohesive point cloud. So how we plan this to be implemented? Well, there's a number of potential approaches, obviously, but what we had envisioned was a centralized approach where you'd have a central computer that would plan the drone paths and accept sensor data from all the different drone participants. However, you could also take a decentralized approach, which might have different advantages, but potentially is a little harder to implement. That's fine as well. The swarm drones will be collecting odometry estimates, location estimates, GNSS, IMU, point cloud data, and then sending that to the other drones. And then the algorithm would need to determine appropriate navigational commands based on the collected data to adaptively fill in voids in the available point cloud data. And this should allow for adding to or filling in gaps in pre-existing point cloud data. So we already have a partially mapped environment. This algorithm should allow for filling in gaps in that existing point cloud. The algorithm should provide a fairly easy to use interface to specify the desired polygonal mapping region that needs to be covered by the swarm. How that's actually implemented is left up to the applicant. And then assembly of the point clouds between the different swarm drones is ideally done using a graph slam approach, just because that's how we've already implemented it in our first version of the software. However, I will specify that there can be a difference here of the online assembly versus the offline assembly. The online assembly doesn't necessarily need to be quite as accurate as the offline assembly. Online, you just need to be accurate enough to coordinate the drones and send them navigational commands and collect the desired sensor data, whereas the offline assembly needs to be exact and give proper results for the single cohesive point cloud. There's a number of challenges that we'll have to deal with in this open call. Obviously computational power on the drones themselves is quite limited. We'll have a Jetson or a Nano or NX or equivalent on board, so nothing more than that. GPS data is unreliable and inaccurate below the forest canopy. The swarm drones might go outside of Wi-Fi range, so we have radio communication available but has limited bandwidth, and meanwhile you also have Wi-Fi, which has much higher bandwidth, but obviously the range is quite limited for that. And so that's going to be another key aspect that needs to be addressed. And then finally, forests are dynamic and fairly noisy environments. The leaves and the foliage of the trees can give inconsistent LiDAR penetration. And so if you scan a tree from one angle and then again from another angle, it's not necessarily trivial to match those 2 point clouds together using like an ICP approach, just because the point clouds of the foliage don't necessarily match up perfectly. So that can be another factor that needs to be dealt with. As well, pre-planned paths that would theoretically cover the forest might not be sufficient because the drones have to avoid obstacles and there might be occlusions due to the different forest elements that require a more adaptive navigational strategy. The developed algorithm needs to be implemented and validated on the SPADE drones. So that's shown on the right here. The drone has 250 millimeter wingspan. It's based on the QAV 250 drone kit by Hollyborough. And it uses the PX4 flight controller. On board, you've got an NVIDIA Jetson Orin Nano computer or equivalent. You've got a Livox Mid360 360-degree LiDAR scanner, as well as GNSS and IMU. And we can add additional hardware as needed, as long as it's within the weight budget of the drone, which is fairly tight, but there is a little bit of potential extra room if needed. Electrical power from the drone batteries is available, which is just 4S LiPo power, so 14.8 to 16.8 volts, depending on the battery charge. And then navigational commands, the drone is just done via ROS2 messaging. For this open call, all the developed software and potential mechanical components must be made open source. For this open call in particular, the algorithm may and probably should be making use of pre-existing repositories. However, it's quite important to note that we do not allow any dependencies in developed code that use the GPL license. So strong copyleft licenses like GPL version 1.2.3 as well as AGPL are not permitted in terms of dependencies. So if you are planning on using any repositories that use that licensing, be aware that that will not be allowed for this challenge. All dependencies must use permissive open source licenses like MIT, Apache, BSD, CC BY, etc., that permit commercial use of the software. A successful system will be able to demonstrate controlling a drone swarm with the SPADE drones in mapping a forest environment. We want to be able to map an open Scots pine forest in Norway, like the image shown on the right, or equivalent. So we're not trying to map, a really dense forest where potentially the drones can't even find a way through. We're not looking for kind of like the easier test environment here where there's a clear path through the trees, but it still does demonstrate that the drones have to navigate through the trees and map the environment. We want to see mapping of a plot size of at least 50 by 50 meters while avoiding collisions with the forest elements and obviously accurately generating the required maps and point cloud data. Applicants will need to deliver 3 milestone reports. Initial report in month 1, where you just outline your plans, timelines, and performance indicators that you're going to use to track the success of the project. In month 3, we want to see a prototype of the algorithm, basically demonstrate the main components of the algorithm where optimizations and minor elements might be lacking. And you need to demonstrate that you can control and connect at least 2 drones in a simplified environment. Basically just to demonstrate that you have made sufficient progress to actually complete the challenge within the desired timeframe. You also have to present a preliminary code base for review and an interim report that just describes your progress, challenges, and timelines forward. And then the final deliverable in month 6 will be system testing and validation that I just described, a final report that describes everything you developed and reports on the KPI fulfillment, and then also the code base needs to be made open source. Further questions? I don't know if we're taking questions now or if I would, but regardless, you can always email me at stefan.lloyd@nibu.no, and I think I'll be taking questions in this webinar as well. Is that correct? Yeah.
We also, Stefan, sorry for intervening. If there is any questions related to your presentation so far, so we can take it. So I think there is one.
Sure.
It's I think no, it's not. It's from the host. Anyhow, Septian, do you know if we have any questions so far?
At the moment, there is no question on the question and answer box. So, yeah.
All right.
Also, one clarification: we can accept questions in the Q&A that we have on the website. There is a link. Okay. And so we will also publish all questions. We will publish all the answers there in the Q&A on the webpage.
Good.
I put one in the chat. You used the term SDU drones. Please explain that.
Oh, okay.
Yeah, no, it's just the SPADE drones that are already presented. Sorry if I referred to them as SDU. SDU is the people who developed them, but these are the drones that need to be used. It's the ones I presented on this slide here, and it's also outlined in the technical guidelines for the Q&A for the open call.
Okay, Stefan, thank you very much.
Yep.
There is one question from Mahdi Danyo. I'm sorry if
All right.
No, his hand is raised, but should I let him or her to speak directly or not? Or just type it on the Q&A?
Let's proceed how we done the last time. So just type it on the Q&A.
Okay.
Because
Please,
we
Mahdi.
will have everything in writing, so we can also publish after that. So it will be good if it's on writing.
Okay, thank you.
Okay, Stefan, let's give them like 2 minutes more, and after that we can continue. Like maybe someone who want to ask something, or just give them time.
While we wait, did you want me to just continue on with the next presentation that I will be giving, or do you want to pass off to someone else?
Or you continue until you finish.
Okay.
So.
Okay, it's Fleming here from Hoffen. I can ask one question since you are kind of requesting it. We have access to some of the really leading companies when it comes to building drones, when it comes to access to forests, and essentially the quality that is necessary to conduct these tests. But from your perspective, what is most necessary there? Because you do also need someone to develop the algorithms. How much will these companies receive from you? How much will be delivered as a package, so to speak? Thank you.
I'm not sure I fully understood the question. You're wondering how much what will be delivered to them?
How much material will they receive from you? Will they receive the relevant software, the relevant libraries,
Yeah.
Yeah.
So everything's open source already, actually. So it's all available to everybody. We'll point them in the right direction, obviously, to it. So, but the developed code base that we already have is open source. The SPADE drones that I presented on the previous slide, we'll be delivering those to them as well, so they have access to that. And then obviously, I would be the one coordinating this open call, so we'd be working directly together, and I would be advising and making recommendations along the way, or helping out if needed. But you know, whatever. I'm always a resource, basically, to help with the development.
Certainly, Stefan. And one thing that we also have discussed in other open calls, it's all right for consortiums to apply for the open call. Isn't that correct?
I don't know. I have to hand that off to one of the other members of the SPADE consortium that might have a better idea of the more, you know,
No,
administrative
actually,
aspects.
yeah, I can answer to that. Consortium are not allowed. It's only single partners, and the maximum funding is 60,000
euros.
for
Yeah.
Yes.
Okay, very good inputs. Thank you. That's all for me.
All right. Thank you. Thank you very much. Is there one other question?
There's one.
So yes, I will read it for you, Stefan. How do I get? So it's one question, and this guy asking, how do I get access to one of the drones here in the UK? We do have access to the forest or something.
So the drones would be sent to you, just via mail. That might not happen right at the start of the project, but you would get them before you need to do any testing. And then for the forest, I wanted to give an idea of what an acceptable forest would look like, but ideally you would find a similar forest near where you are geographically that would facilitate testing. So it just needs to be a forest that has, you know, it's a forest, it has trees, but not necessarily trees that are so dense that it's difficult to fly through. I think in the UK there are quite a few forests that would be, you know, somewhat similar, as long as there's areas that you can fly drones in. Otherwise, you can always come to Norway, but it's a little bit further for you.
So I think there is no other questions. So Stefan, you can jump to the other session that you have. Anyhow, I will let the participants in this call that they can keep asking and yeah, or during all the presentation. All right, thank you.
Can everyone see my next presentation here?
Yes.
Great. Okay. So the next challenge that I'm going to be presenting is the ultralight self-leveling landing gear for quadrotor drones. So again, we're looking at doing enhancing the use of drones in forestry management. And one of the problems that we often have is that the steep, rough, and uneven forest floor terrain in forests is a problem because we can't take off and land the drones appropriately in that kind of environment. So we're looking to address that with the challenge ultralight self-leveling land gear for quadrotor drones, where we would make, you know, self-leveling landing gear for drones working in forestry. So what we're looking for is an open source design that will be scalable to different types of drones that could be small drones or large drones. However, the applicants will be required to validate this design on 2 SPADE drones. So you'd have a medium-sized drone with a wingspan of 0.5 meter and a large seedling planting drone that would have a wingspan of 1.3 meters. But approximately the design should follow the style shown on the somewhat rough mock-up on the right there. That's mostly just there to show kind of the placement of the different design elements, but you'd have your regular quadrotor design. And then what we're looking for is to have a leg directly underneath each of the rotors. And that leg would be a sort of telescoping lead screw assembly, potentially. There could be other solutions to this, but this is kind of what we had envisioned to be the simplest and most straightforward approach. So basically what you do is you'd have a carbon fiber kind of tube slash box that would contain a motor and potentially the electronics that are necessary. And then that motor could just extend and retract the lead screw as needed, and that lead screw would have a little foot on the bottom. So basically just by extending and retracting the lead screw, you could level the drone appropriately. Obviously in the sketch, it's a little simplified. You need to have some bracing of the arms and potentially cables going between the different wings of the drone. But that is the kind of the approximate style we're looking for. As mentioned, the designs that will be published and made open source need to be scalable. So we want this to be designed in such a manner that there is a solution for a small drone, there's a solution for a medium drone, there's a solution for a large drone. The design should be obviously as lightweight as possible. This is going on a drone, so we want to use carbon fiber tubing, we want to use lightweight motors, etc. For computation, the drones will have an onboard Jetson or a Nano or an X equivalent. All software must be packaged into a ROS2 humble Docker image, so that's nice and portable. And then the validation of the drone will be done, the validation of the design will be done on at least 2 SPADE drones. You have the medium-sized drone, which has a wingspan of 0.5 meters, that's motor to motor. And then there'd be a combined load capacity of the legs of 26 kilograms for that drone. The onboard power that's available is 12 volts, 5 amps, or 6S LiPo power. And then for the large seedling planting drone, you have a wingspan motor to motor of 1.3 meters, a load capacity combined on the legs of 60 kilograms, and 12S LiPo power, or 12 volts, 5 amps. Applicants will also be expected to develop a somewhat basic self-leveling control system for the hardware they develop. And this should follow the strategy of basically using a downward-facing LiDAR scanner to determine an approximate configuration for the legs to be in as it lands. And then during the actual landing process, we would use feedback from the leg contact sensor in real time to basically correct for errors in the initial estimate from the LiDAR scanner. You can use an IMU sensor as well for that. So the drones themselves have an onboard IMU sensor that can detect tilt, obviously, and also a downward-facing LiDAR sensor, which would be a LiveVox Mid360 sensor that can be assumed available to scan the ground. The developed leg solution must also have some way of detecting ground contact. So this could be a strain gauge that is somewhere on the mechanical design of the system that can detect loads. It could be some kind of fancy current measurement from the motor, although you'd have to eliminate friction forces, so that might be a little tricky. Or it could be something as simple as a contact switch, which might be, the easiest approach. And then also the solution must have absolute feedback for each leg position. So ideally without requiring homing. So basically you would likely have an absolute encoder on the back of each motor. As before, all the software must be made open source using a permissive open source license like MIT, Apache, BSD, CC BY, etc. You can make use of pre-existing repositories, but you cannot use repositories as a dependency that use the GPL version 1.2.3 or AGPL licenses. And then as a completion criteria, a successful system must be demonstrated during takeoff and landing with a ground height deviation at the landing site of at least 20% of the drone's wingspan for each of the 2 drones. So that's 100 millimeter for the medium drone and 260 millimeters for the large drone. And during takeoff, obviously, the safe angle of the drone body needs to always be maintained. Applicants that are successful will have to deliver 3 milestones as before. So month 1, initial report that reports your plans, timelines, and performance indicators. In month 3, you need to present preliminary design documents, so basically more or less complete mechanical and electrical design documents that are not, physically made and tested yet. You'd have to present a preliminary control software code base and an interim report that just reports on your progress, challenges, and path forward / timelines. And then the final deliverable in month 6 would be showing that this system is tested and validated, making the code base open source and documented, and then delivering a final report on the developed methods and modules and reporting on KPI fulfillment. Again, further questions you can ask me or the Q&A, and we'll post everything online. Otherwise, you can always ask it now if there are any questions.
So yes, we have two questions. One is related also to hi, do you provide drones for testing and implementation?
I think depending on where the applicant is, we would either send the drone to them or have them come here, or just send the hardware here and we could test it. It kind of
Okay.
depends how far from Norway they are. So we can probably take that as it comes.
So it's another question. Are we required to go to Norway for testing?
Yeah, I think that kind of ends up going in the previous one. I think if you live really far away from Norway, then we would just have you demonstrate that the functionality is there, and then we could test them here in Norway, or we would ship the drone to you. We can maybe determine what the easiest solution is based on the situation of the actual applicant in question. But either we'd ship the drone to you and get them tested, or the drone would be shipped to us and we would test it.
Okay.
I don't think it would be required for you to come to Norway physically.
All right. So I will read another question for you. Is the thruster motor part of the telescopic leg? If not, would we be provided mechanical interface data?
By thruster motor, do you mean the rotor itself, like the
I think so. Yes. So they are referring to that.
Yeah,
Thank
so
you.
no, the telescoping leg would be attached to the thruster motor. Yes, we'll be providing mechanical interface data, although I think for the purpose of the initial applications, that's not super relevant. And in fact, we haven't designed that aspect of it yet. It's something we could design in tandem together. And we would manufacture our mechanical connection, and you'd manufacture the leg connections. I think there's more that needs to be done, in the sense that there needs to be bracing and cabling potentially. So I think the way to go forward there would be that the applicant would suggest a mechanical interface. We would provide CAD of the existing drones, and we can then make modifications as necessary to provide an appropriate mechanical interface, because we'll be working on these drones from our end as well. So there's flexibility there. It's not a fixed mechanical interface, but so we would probably just work together at that point with the applicant to find the best solution, depending on the design that they wanted.
Okay. Yeah, we don't have any other questions. So it's another one now. Can you give a range of what do you mean under ultra lightweight?
I think what I mean by that is just that every reasonable step to make the mechanism lightweight is taken, and this will be evaluated in your proposal. You're going to make a proposal that you'll submit, and we will evaluate these proposals, and we'll go with the one that is best suited, as determined by third-party evaluators. So how light that solution is going to be one of the key factors. The weight in general will depend on what size of drone it's implemented on. But as long as you're using like carbon fiber material, aluminum for metal components, otherwise lightweight solutions, I think that's kind of what we're going for. Obviously, we can't make this out of steel because it's going to be too heavy. I think for the large drone, you'd probably end up being in the weight range of 2 to 3 kilos, maybe lighter if you can. For the medium-sized drone, it'd probably be a little lighter than that.
Thank you, Stefan. Yeah, it's let's hope that we'll have let's wait 1 minute more in order to jump to the other one. This is a message for applicants. We encourage you to put many questions. For that reason, we have these info days as well. So please feel free. Okay, anyhow, if there are any question now, we can answer in the next Q&A session. So, all right, Stefan, you have anything else to present, I think?
Yes, I've got one more open call. Lots of open calls for me. Okay. This is the last one that I'm going to present. Can everyone see slides? All right.
Yes.
So the last challenge that I'm going to be presenting is below canopy forest data collection and annotation. So again, we're looking at using drones in forestry management. Forestry operations rely on continuous detailed inventory and monitoring of the forest. And a key part of this is becoming AI tools. But developing these AI tools require large training data sets that are otherwise, somewhat difficult to come by. So for this open call, what we're looking to do is to collect and annotate below canopy data sets, both in image/video and point cloud from forests throughout Europe. So the SPADE consortium members will be collecting data sets throughout Europe that will be provided to the applicant to segment and annotate. And then the applicant themselves will also be required to collect local forest data sets using a provided data collection module that we will give to them. For this open call, it's quite critical that applicants must show that they have experience labeling and annotating foreign censored data because the quality of the data is going to be very critical to us in this open call. How this will work, there will be annotation of point clouds and video streams from a minimum of 10 plots, where a plot would be like 50 by 50 meters of forest. Additionally, there'll be a minimum of 200 short 30-second video streams that must be annotated. However, applicants will put together a proposal, and applicants that are capable of labeling higher amounts of data will be preferred in the selection process. Point cloud annotation will involve segmenting out individual tree instances and labeling broad classes, so not detailed classes, kind of like just several broad classes like wood, leaf, ground, deadwood, etc. Contrarily, if for the image data sets, you'll have a bit more classes that you need to label. They'll be a little more fine-tuned, so you'll have things like grasses, bushes, mosses, lichen, etc. Applicants will also be required to collect their own data sets. They'll be provided with a handheld data collection device where you just need to walk through the forest. And with that, a minimum of 4 plots, 50 by 50 meters, must be collected of different various forest types from their local geographical region. Labeling of the data must be done in a 2-stage approach where you have labeling and then internal review of the data for quality control. The data collection itself will be done using a data acquisition system that's being developed within SPADE. Progress on that is ongoing, but it'll basically just be a handheld system that integrates a battery, onboard PC, GPS, camera, LiDAR, and IMU. And you just walk around the forest with this, making sure to have full coverage of the forest area. And that will give you a fairly large raw data set from the sensors. You will send that to us. We will assemble it into a point cloud for you, and then send back, a last file that you can annotate from there, as well as the video streams from that data set. Data labeling will be done using Darwin V7 software for the image and video data. SPADE partners will provide the licensing for this software. And then annotation of the point cloud data will be done using Cloud Compare. That's open source, so everyone has access to that. All the data sets must be made open source and fully documented, and then the challenge would be considered complete when all the data is collected, annotated, reviewed internally by the applicant, and then reviewed for accuracy by the SPADE partners, which in this case will be Nebio, us. There'll be 3 milestones as always. An initial report where you outline your KPIs, timelines, methodologies. A halfway report in month 3 where we want to see the locally collected data sets that are maybe not annotated yet, as well as interim labeled data sets. So you should submit about 30% of the total data that is to be annotated for review to SPADE partners, and an interim report that describes your progress, any challenges, and timelines forward. And then the final report in month 6 will be making the data sets fully documented, open source, and a final report that documents the data sets, reports on your work, and on KPI fulfillment. And as always, I'm open to questions now.
Okay, thank you, Stefan. Let's wait 1 minute because there are no open questions.
Yep.
Q&A is closed. We cannot raise any question in the Q&A.
Yeah. Okay, Fleming here again. It seems like it's not possible to type in questions right now. Could you perhaps tell us something about what kind of stakeholders you are most interested in? Thank you.
I'm not sure I understand the question. What do you mean by stakeholders?
Well, for instance, a typical stakeholder, it may be a forest manager, it may be forest owners, it may be others that are responsible for what you can call culturing the forest, if you like. Thank you.
Yeah, I think this is maybe one step removed from the end user because the stakeholders here would be mostly researchers and organizations that want to develop using these data sets. And then they would be developing the actual tools that would be used by forest owners or governments or other organizations that are doing forest management. So I think, yeah, we're one step removed from the end user here because they're not using the data sets directly. It would be more for researchers and developers.
Great, thank you.
I have a question. Forest types. By that, I just mean the dominant types of trees that are in the forest need to be somewhat diverse. So if you have pine forest near where you live, ideally you don't have 4 plots of identical pine forest. Go for different types of species if you have different types in the area.
Yeah, I don't think there's any other questions, Stefan.
Great.
So
okay, that's easy. All right, so I will stop sharing my screen. That's everything for me. Thank you for your time.
Yeah, thank you, Stefan. It was an interesting presentation. Thank you very much. Okay, so let's start with the other one. Please feel free, Stefan.
I don't have any more presentations, so.
I think the next one is Emad or Thor. Want to start?
Yeah, it's Emad.
All right.
Okay, let's see. Can you see my slides full screen?
Yes, we see the full screen. Yeah, one slide.
Super, thanks. Yes, good morning. I'm Emad Eveit. I work at the University of Southern Denmark as a professor, and I will show you the CH2 open source tilted rotor drone system. So the agenda for this presentation is what is the SPADE open source hardware and software architecture. It's important to understand this because the challenge is how to expand the architecture to add the new software and hardware to make the tilted rotor drone. Why we need it? So then it's the second part, the use cases and what are the objectives of the open core. And the drone development, the expected ones, and the deliverables at the outcome of the open core. As Stefan mentioned, we have the SPADE drone that has different components. And I will try to point to here. Yes. So you can see this as many layers of development. So we have the hardware layer. We speak about the airframe here. So basically motors, propellers, and the carbon fiber to represent a drone frame. By having this, you can control the motors somehow, then this frame can lift, but doesn't do much. But if you want it to be controllable, then we add the flight controller. And here we use in SPADE Pixelhawk flight controller with Pix for autopilot. So that is our open source hardware and software that we used from previous EU projects. By having these 3 units together, you have a controller with a flight controller and the airframe. This drone can fly manually. To get it to fly automatically, autonomously, then we need an onboard computer. In SPADE, we work in these 3 different types of computers. One is CPU-based, Raspberry Pi, GPU-based, an NVIDIA Orion, and an FPGA, which is an MBSOC. Has a CPU for running ROS, and has an FPGA to accelerate some of the heavy computational tasks. These 3 units are a part of the platform in the sense of they communicate with the flight controller to steer the drone instead of the ground station or the remote control. Based on which data, there are sensors that are interfaced with this onboard computers to sense the environment, take decisions, and then the drone is controlled by some control loops that running on this onboard computers. As you heard, also have the swarm aspect in the project. So we have also drone-to-drone communication. You can see that as a communication between the onboard computer to one drone to the other onboard computer and the other drone. You also hear that the SPADE has a cloud and digital twin, and then also here we have the communication with the onboard computer and the cloud server to upload the data. This is our SPADE architecture that is also left to open source, so you can also go and see it. I will show you where to find it. And that is one example, and we have many different types of drones in the project. In that case, we have 360 LiDAR communicating with the onboard controller here as an NVIDIA card, and that is communicating with the PX4 Pixelhawk flight controller that is underneath here. So one could make an algorithm to let this drone fly based on the data coming from the LiDAR, and then say what exactly should be the task, avoiding obstacle or run a slam algorithm, and so on. When it comes towards onboard computer, there are many aspects one has to be aware of. If you use a Raspberry Pi, like a CPU-based, that is fast to develop, but you get a lower performance compared with a GPU or compared with an FPGA. Depends on the task at hand and how much time you have. In addition, also there is a power consumption. FPGAs will speak about 1 watt if you want to run a neural network. GPUs, I would say 15 to 30 watts. CPUs, they can go higher, or even they cannot really run heavy tasks. So it depends on the requirements, and also depends on the space. We work with autonomous drones, so the space is quite a factor with us. So we need always the smaller cards. To have a look to the SPADE drone hardware and software architecture. So it is available under the Eclipse website, in which also they run also the GitLab, which is owned by Eclipse, and Eclipse, as you notice, it's a part of the project. And we have the open source repository for the drone architecture under SPADE. So you can click on that link or search under Eclipse for the SPADE project, and then you'll find this documentations. For the use case, we saw a classic drone can go up and down, right and left, and no more. And this is a challenge how we can get it to fly 360, so going around itself. And this can be done by tilting the rotors. Tilting the rotors means we don't have a straight line for connecting the propellers and the motors, but we have a tiltable end of the motors here. So imagine this motor is not in a fixed position; it's rotating around the axis here. And this will be done by adding different, you need to make a mechanical design, which is a part of the challenge, in order to put a motor that is controlled by the onboard computer to rotate the propellers to do something called vector thrust. So the drone is not following the classic control bars to go up and down, but it's like vector. They say, I would like to go 20 degrees, so all of the propellers are going to tilt in a certain direction to give you the 20 degrees rotation. In a classic drone, that is not possible. It can only go up and down. Yeah, so that is basically the mentality, the idea, how to get this drone to rotate in 360 degrees. And that is important for SPADE because we have to monitor different terrains that they are difficult to follow. So it's not always straight lines, they are in slopes. And a part of this also, if we can interact with the ground that is not in a straight line, we can also do, imagine planting, or we can take samples of the grounds or checking different trees if we can operate in 360 degrees. And that is the mentality to have this types of orientation of the drone. What is the requirement? We need to have it to be a fully functional drones. Basically, you have the hardware to tilt the motors, and also the software code that is integrable with PX4. I think also under PX4 you can find some initiatives that you can use in order to make the tilted rotor. This has to be done in real time, so the computer, let's say, if you use a Raspberry Pi, maybe it's not going to do it in real time. It's a software, so maybe it will be delayed. But maybe you need to think about real-time processors that can do the work. Maybe in some types of Raspberry Pis or NVIDIA cards or FPGAs, there will be the efficient processors to run the control loops in real time. When you also work on this, you need to deliver the outcome as open source. That is very important because we also work in open source communities, so we expand our open source hardware and software architecture with a new feature, the tiltable rotor drones. I put here two references. One is a paper that you can read about how this is designed, and also see some other groups made some work related to PX4 for tilting tiltable rotor drones. What we expect from you to deliver? So we have 3 checkpoints: months 1, months 3, months 6. Months 1 deliverable. Here we speak about defining KPIs that we need to agree with the SPADE representative. KPIs to say, my months 3 KPI is to test the drone in the lab. That could be a KPI. Or I'm testing it in 180 degrees first step, and then I go 360. So these types of KPIs. So you define the KPIs, and then we discuss it with us, and then we agree if they are realistic KPIs or not. From the start, you need to contribute to the GitLab repository under Eclipse. So basically, when you develop codes, you push it there, and then we can have a look, and this is the progress of your work. It has to be, as I said, has to be open source, and it will be accessible by the community. In month 3, you have the interim report. So you write a documentation how we are going towards fulfilling the KPIs, and showing a video demonstration of this drone flying in a lab environment. In the last part, in month 6, we have the final reports covering all of the KPIs, testing the drone in outdoor environment, and sharing the code for the controlling the drone, but also the 3D models for building the tiltable part of the drone. And all you put it in the SPADE GitLab repository. And that is also the summary here in the table, months 1, month 3, and month 6. Yeah, that's it.
Thank you. Thank you very much, Amanda. So let's see if we have any questions. For now, we don't have any open questions. Septian, please confirm me that the participants can put questions there.
Yes. Yes,
So,
everyone
all
can
right.
put, except
All
the
right.
panelists.
So, Emma, let's wait 1 minute or two, like the participants to insert any question if they have. Anyhow, meanwhile, I want to wrap up the things. So, guys, you observe that you have to deliver us 3 deliverables. One is in month 1, interim initial report. After that, we have the interim report and the final report in month 6. The payment that you receive will be done after the first interim report. I mean, you'll deliver the interim report in month 3. We'll make the first payment somewhere in month 4, like you to know, and the first payment will be half of the money that you receive for your project. And of course, the last payment will be done in month 7, because in month 6 you'll deliver us the final report. So after that, we'll do the payment. So we'll be somewhere in the beginning of month 7, like you to know, for your calculation and so on. So yes, I think there are no any other questions. Anyhow, you have our contacts. Please feel free to inspect our website. Don't forget that you can apply until 26th of May at 5 p.m. That's the hour and the deadline for this open call.